Hello and welcome back. My name is HyderAbbas. In this video, we will understand about the JVM architecture, which is very crucial if you are learning Java. So far in this entire playlist, we could able to complete the fundamentals of Java. We have also completed the fundamentals of OOPS. Before we move ahead with the static concept, inheritance and the other concepts, it's time to understand more on the JVM. It is very crucial. Even if you are working with languages such as Scala, Groovy or Kotlin, which fall under the JVM language family, you also might have heard about JVM, and then also it is very crucial for you to learn about JVM architecture. And most of the learners or developer don't think much about the JVM's inner working until something goes wrong or the performance needs the optimization. So understanding JVM mechanics is very crucial when debugging or optimizing your Java based application. So basically in this video, we will get into the JVM's architecture. We will understand all the major components and how everything works together to make Java program run seamlessly on various systems. Fine. Also, earlier in this entire playlist, we had already covered the concepts such as the heap memory, runtime stack area, which is the stack area of JVM, data areas. After this particular video, I would ask you to please watch that video also so that you can understand these things practically. Going forward from the next video, once we start the journey of static variables, same JVM architecture we will see in practical approach also. Earlier, heap area and the runtime stack area we have understood, and the other components in this video we will understand, and in the next video also we will understand more on this. Fine. So as you all know that whenever we write a Java code, we save that Java code with .java extension, and then we will give that to the Java compiler, and Java compiler converts this Java code into bytecodes, which is intermediate level language, neither in high level nor in the machine level. It is the bytecodes, and wherever bytecodes are present, we call that as .class file. .class file means it contains the compiled Java code. That means compiled Java code referring to the bytecodes. And that bytecodes will be given to the JVM, which is Java virtual machine. And then JVM internally makes use of some of the components, especially the interpreter, and convert these bytecodes into machine understandable format, which can be run in any machine, whether it could be Windows, Mac or Linux, which makes Java as the VORA, write once, run anywhere philosophy works here, because JVM abstracts away the underlying hardware and the OS specific. As you all know that machine level is always platform dependent. So what happens here is Java code will be compiled to the bytecode, which is platform independent. That code can be executed in any platform, and that will be given to the JVM, and JVM is the one who will convert that bytecode into machine understandable format, or you can say machine level language. Now how exactly JVM takes this bytecode and execute into machine understandable format, or how JVM executes the Java program is what we need to understand here, because once we compile the Java code, the bytecode will be handed over to JVM, and it is the JVM who executes the Java code. And how exactly JVM does is what we need to understand here. So basically we have three major components here in the JVM architecture. Number one happens to be the class loader subsystem, which actually prepares the Java classes and loads them into the memory. So class loader is responsible to load all the bytecodes, which is Java code which you have written, right? That has been compiled to the bytecodes. Those bytecodes will be loaded into JVM's ecosystem for the execution. Class loader is responsible for this, and more on class loader also we are going to understand here. The next major component comes here is the runtime data area, which is method area, heap area, stack area, PC register, native method stack. Earlier in our series, we have understood about the heap area and the stack area. So basically it holds the runtime data. If you have already watched my videos on heap area and stack area, you might know. If not, again in this video also I would like to clarify the same. And one more major component in the entire JVM architecture is the execution engine, which has the interpreter and just-in-time compiler which executes the Java program. So basically the conclusion here is, before we proceed further, JVM is the one who executes the Java program. And how JVM executes? JVM internally makes use of three major components. Number one, class loader. Basically, it will load the entire code into its ecosystem. And by using the runtime data area, it will keep all the components of your code which you have written into different areas: method area, heap area, stack area. Then using the execution engine with the help of interpreter and just-in-time compiler, JVM converts this bytecode into machine understandable format, converts that into machine format that will be given to the underlying platform, which will take care of the execution here. Now let's understand the same thing one by one here. Fine. So number one happens to be the class loader. So the class loader is responsible for loading the Java classes into memory. Classes are first compiled into bytecode, you all know that, then loaded into the JVM by the class loader itself, where we have three important components here. Number one is loading, number two is linking, number three is initialization. When it comes to loading, the binary bytecodes, whatever bytecodes we have of the class, that will be loaded into the JVM's ecosystem. During the linking stage, the dependencies of the classes are resolved. All the verification, preparation and the resolution will come into picture here. And finally, in the initialization stage, the static components of the class, static variables, will be allocated memory on the heap area. And if there is any static initialization block, that will be executed. We have not yet seen about the static components in this entire playlist. From next video onwards, I'll be taking care of the static components and non-static components. Same JVM architecture again I will discuss by writing the Java code also. Fine. So basically here in the class loader subsystem, we have three things: loading, linking and initialization. When it comes to loading, in this stage, the entire bytecodes gets loaded. How it gets loaded? For which three again important classes comes into picture here. One is bootstrap class loader, extension class loader and application class loader. That is what we need to understand here. Coming to the bootstrap class loader here, which is a parent of all other class loaders. It is a part of class loader subsystem. If you have understood the general idea about class loader is to load the entire bytecode into JVM's ecosystem, and if there are any static components, memory will be allocated for that. Apart from that, if you want to understand more, is what I am discussing here. Coming to the loading, linking and initialization stage. Coming to loading, we have three loaders here. Number one is bootstrap class loader. So as you can see, the bootstrap class loader is the first class loader that is involved in the loading classes into the JVM. It is responsible for loading the Java classes that are part of Java standard library. Whenever you are downloading the JDK from the Oracle, from the internet, you will be having all the library files, the JVMs, the entire kit which is responsible to execute the Java code, right? And all the predefined classes which comes under the java.lang package, util package and other package, which is basically part of rt.jar. rt.jar means such a jar file which has the predefined Java classes, or you can say library classes which Java team has coded for you. So bootstrap class loader will load these entire classes into the JVM if you have used here. Example, if you have used scanner class, or maybe if you have used the string class, predefined string class, this class will be loaded into JVM by bootstrap class loader during the class loading system. Fine, during the process of the class loading. Then we have extension class loader, which is a child of bootstrap class loader. It is responsible for loading the classes from the Java extension library. That means apart from the predefined classes, if you are using Java X means servlet or anything which is other than Java. Right now, Java X, all the predefined classes which supports Java, apart from the core Java library, Java X earlier, now it is owned by Jakarta, right? The owner of Java extension predefined classes right now is Jakarta. All those extension classes which you are using in your Java application, that will be loaded, right? into the JVM ecosystem by the extension class loader. And then we have the application class loader. It loads the classes which is specific to application, whatever classes which you have coded apart from the predefined classes, from the Java extension library, whatever code which you have written, that will be loaded into the JVM's ecosystem, whatever class it could be, example my class, or whatever code you have written apart from the predefined code, that will be loaded into the JVM's ecosystem. So basically, during the class loading, three important stages are there. Number one is loading. Loading again subdivided into three parts: bootstrap class loader, extension class loader, application class loader, right? And in three stages also, all your Java code which is there, that will be loaded into JVM's ecosystem. And how it will be loaded is what we have seen here. And then we have the linking and the preparation stage. In the linking stage, it will verify, it will ensure that the bytecode is valid, adheres to the JVM specification, no illegal memory. It will just verify everything, if all the code and every structure is correct or not, right? And during the preparation stage of linking, allocating the memory for the static variables, setting the default values for the static variables, and by chance, if there are any static blocks present in your code, that will be executed here itself during the linking. Under that, we have a preparation stage. During the preparation stage, then we have a resolution, resolving the symbolic references like method calls. Example, you have stored a variable, and that variable again you are using inside a method. All that referencing, linking will be done during the resolution stage of linking. Then we have the initialization, where static block gets executed, and inside the static block, if you are assigning any value to a static variable, that will be also assigned during the initialization block itself. Static variable earlier used to get allocated memory in the method area, but after the Java 7, the memory for the static variables will be allocated on the heap area. And usually we use static block to initialize the data to the static variable. What is that? In the upcoming videos of static keyword, you will understand here. Fine. So just to conclude here, before I proceed further with the JVM's runtime data areas, under the class loader subsystem, the entire code gets loaded. And if there are any static variables, memory will be allocated in the heap area. And if there is any static block present in your Java code, that will be executed. Then comes the JVM runtime data areas. We have many data areas here: method area, heap area, stack area, PC register, and native stack area, native method area. Now, whatever code which is getting loaded, entire code will be kept in the method area. When you create the object, then the memory for the object will be allocated on the heap area. And if there is any instance variable, memory will be allocated on the heap area. If there is a static variable, during the class loading itself, memory gets allocated on the heap area. And if there are any methods or anything which is getting executed in your Java code, it is happening on the stack area itself. If you are invoking a method, that method gets loaded onto the stack area. On the stack area, the execution of that method is happening. If there is a block, and if the block is getting executed, that block gets loaded onto the stack area. One stack frame gets created, and that will be executed on the stack area itself. More on heap area, more on stack area, already we have discussed in our previous videos. Okay, you can also refer there. Just to summarize this, so we have a method area, stores the class level data like method code, constants, metadata. This is where the entire code after JVM loads will be kept in the method area. Then we have a heap area, stores all the object. Whenever you create the object, you create the instance, memory will be allocated on the heap area. And inside that memory of the object, instance variable memory also will be allocated. And if there are any static variables, memory also will be allocated on the heap area itself. Coming to the stack area, as we have seen earlier also, whenever you invoke any of the method, any of the block, constructor, anything which gets executed, that will be loaded onto the stack area. And on the stack area, that gets executed. And if there are any local variables which are there, that for memory for those local variables, reference variables are also allocated on the stack area. Fine. And every time methods invoked, a stack frame is created. what exactly this is, what is local variable, what is instance variable, how method execution happens on the stack area. In this playlist, I have explained clearly by writing down the Java code. I would ask you to go back to the playlist and understand two videos wherein I have talked about instance variable, local variable. Also, I have talked about the method execution. It will give you better idea on the heap area and stack area. And as a Java developer, it is must for you to know better about the heap and stack area. Detailed discussions have been done in our playlist earlier also. Now, coming to PC register, it will hold the address of each instructions which to be executed going forward. So PC register will maintain the address of every instruction which to be executed. And coming to the native stack area, whenever you are using such a library in your Java application which is coded in the languages such as C or C++ other than Java, for such code, memory will be allocated on the native method stack. And this is the use of the 5 important runtime data areas. Out of 5, 2 are very important which you must know, which is heap and stack. Earlier, by explaining the code of instance variable, local variable and method reference variable, I have discussed with respect to code also. Please do watch in this particular playlist. Great. And then we have the most important part, which is the execution engine, the one which is responsible to execute. Basically, JVM internally use interpreter to execute the Java code. Basically, JVM use interpreter to execute your bytecode into machine understandable format. It will convert the bytecode into zeros and ones, binary format. And interpreter will convert your bytecode into zeros and ones by following line by line. Interpreter means line by line, compiler means at a time, at once. And since internally JVM uses interpreter, it will convert your entire code line by line into the binary format. And then we have just-in-time compiler, which is used to support the interpreter. Every time JIT compiler will not be used here. It is there to support the interpreter when it will be discussed. We shall be discussing. And garbage collector, on your heap area, whenever there is an object, there is an instance for which there is no reference variable, automatically in Java, garbage collector will be used to deallocate the memory for the object whenever object becomes the referenceless. And this also practically in the same concept of methods I have discussed. Please watch that also. Fine. So now just to give the points on this also. So let me just add this. Interpreter reads the bytecode line by line and executes it. Convert that to binary format and execute this. It is very simple to implement. It is slow execution. Why? Because interpreter executes every code line by line. And when it comes to just-in-time compiler, whenever we have frequent code calls, if there is any loop which is invoking method multiple times, and in that case, if you go with just no interpreter directly, again it will convert that into line by line, zeros and ones, line by line. It will take a lot of time. It will slow the process. To help the interpreter in frequent calls, we use just-in-time compiler. All of these things are by default implemented behind the scene. As a developer, you need not to do something for it. Whatever is already happening behind the scene is what we are understanding here. Fine. So just-in-time compiler will convert a frequently, invoke code into zeros and ones at one go, because it is compiler. And interpreter does that line by line. And usually whenever we have any loop or something, which again and again has to get executed. In that case, just-in-time compiler will come into picture and support the interpreter for the code execution. And when we have a garbage collector, which we have already discussed here, whenever there is a referenceless object present inside the heap area, memory will be deallocated by the garbage collector automatically. You need not to do anything on that. You need not to write a code or invoke garbage collector to deallocate the memory for the object, to deallocate the memory for the instance. And we have JNI, the extra which you have seen here, component. native method interface and native method library. So whenever we use the code in our Java, which is not coded in our Java application, which is from the C or C++ other backgrounds, right? In that case, in order to execute that, Java's interpreter or just-in-time compiler cannot be used. In that case, Java native interface is used, which allows Java to interact with the native code written in languages such as C or C++. Very often you might not see this unless you have used some of the libraries or some extensions which are coded in the other languages. Usually internally it uses interpreter, which will convert entire bytecode into a machine understandable format, line by line, one by one. And to support the interpreter, sometimes just-in-time compiler gets used here. Fine. Just to summarize here, JVM has the important components. Number one, class loader, which loads the entire bytecode into the memory and also allocates the memory for the static variables on the heap area, and if there is any static block, that gets executed. Then we have our runtime data areas, stores memory for the object. Whenever you create the object, inside the object, memory for instance variable, and inside the heap area, static variable memory will be allocated. And whenever you invoke the method, that method stack frame gets created on the stack area, and if there are any local variables, memory also will be allocated on that stack frame itself inside the stack area, and the entire code will be kept within the method area. These three areas are very important of JVM runtime data areas. An execution engine executes the Java program by making use of interpreter and just-in-time compiler. And garbage collector is used to automatically deallocate the memory whenever object becomes referenceless. And we have a native methods which enables the interaction with non-Java code via JNI. And this is the basic summary of the entire architecture of the JVM, which we have seen. And I would also suggest you to watch my previous videos wherein we have discussed about heap area, stack area, garbage collector, three important components of JVM practically by writing down the code. Same we will understand in upcoming videos of this series, wherein in a class I will have both static components and non-static components, static variables, non-static instance variables, static initialization block, non-static Java initialization block, constructor, static methods, non-static methods. Basically all possible components which can be there in a class, I'll be writing that in an application, and I'll consider the heap, stack area, and we shall understand what exactly happens behind the scene in the memory. Earlier about methods, instance variable, local variable, reference variable, heap area, stack area, garbage collector we had understood practically. Now we need to understand more in the upcoming videos. And this is the general overview about the JVM architecture. Thank you for joining me in this video. We shall understand more on this in upcoming videos of this series. Thank you everyone.